Today we are going to be talking about a novel and sustainable plasma route for green ammonia production. We are thankful to the Chinese Academy of Sciences and Korea Institute of Machinery and Materials to provide an opportunity to share our work. First, we are going to introduce environmental problems and their solutions. Then we'll talk about the production of hydrogen and NOx from water with nitrogen discharge. Then we'll talk about how we can utilize this hydrogen and NOx to produce green ammonia. Finally, we'll talk about the reaction mechanism. We all are facing some global problems like global warming problem due to greenhouse gases, our dependence on fossil fuels, increasing energy demands. We have a solution of renewable energy, but it also comes with its own problems, like peak powers and energy transportation issues. We all know that fossil fuels, oil and gas can easily be shipped and stored, but renewable energy can't, preventing it from becoming a bigger player on the world market. That's why we are trying to convert renewable energy into liquid ammonia, which would allow renewables to be shipped and stored. But the current process of creating ammonia is anything but green. So we have introduced a new concept to make truly green ammonia from water with nitrogen discharge plasma from renewable energy. In this study, we developed a novel, continuous, scalable, and single-step plasma catalyst integrated technology for ammonia generation via a hydrogen and NOx intermediary approach. Our approach is based on the coupling of two technologies. First, water splitting in the nitrogen discharge using a rotating gliding arc to produce hydrogen and NOx. Second, intermediary NOx reduced viaduct hydrogen to produce ammonia in the presence of noble metal catalysts. Nitrogen was tangentially fed into the reactor through two holes at the bottom of the cylindrical ground to provide a swirling flow to rotate the arc. In this unique system, liquid water was introduced in the form of a water film into the nitrogen discharge from exactly the center of the surrounding wall of the reactor. This form was used to assist in reactor cooling and not destabilize the arc. The arc discharge was driven by an AC power source with a high voltage transformer. The highly energetic electrons and active nitrogen species collided with the water film and ionized, dissociated into hydrogen and OHO radicals. The OH and O radicals further reacted with the nitrogen radicals to form NOx. The generated NOx and hydrogen were injected into the palladium catalyst on a ceramic monolith connected to the plasma reactor. The NOx was completely reduced by the cogenerated hydrogen to produce ammonia with high selectivity. Figure shows the hydrogen, oxygen, and NOx production rates during water splitting in the nitrogen discharge as a function of the specific energy input. The continuous increase in the specific energy input increased the hydrogen production rate, which confirmed that no secondary reactions with hydrogen occurred during plasma water splitting. In addition to hydrogen, oxygen also formed during water splitting and followed the trend of stoichiometric water splitting at a low specific energy input. However, the oxygen production rate began to decrease as the specific energy input was further increased until it was ultimately completely removed. The disappearance of oxygen with a high Ca indicates the presence of secondary reactions involving O and N atoms. This assumption was confirmed by FTIR. The presence of NOx was observed in the FTIR spectra. We demonstrated that hydrogen and NOx can be generated by water splitting with a different hydrogen to NOx ratio. These are essential feeds for N production. To investigate the catalytic reduction of NOx, the catalyst was connected to the outlet of the plasma reactor. Catalytic reduction was carried out at 110 degrees Celsius, and the reaction temperature was maintained by the heat generated from the plasma reaction that was tuned by controlling the pipe length and flow rate. Figure shows the NOx conversion and concentrations of N2O and ammonia as functions of the specific energy input. At high specific energy input, the NOx to N2O conversion sharply decreased to zero and the generated NOx from the plasma was completely converted to ammonia with an almost 95% selectivity. In addition to ammonia production, the remaining water after the plasma reaction contains nitrates produced from NOx interacting with the water in the reactor. Water with nitrates, which is known as plasma-activated water, is an effective plant fertilizer. Figure shows the effect of the specific energy input on the ions production rate in water. The nitrates concentration in water was high at low specific energy input as the water solubility is high at low temperature conditions. However, as the specific energy input increases, the nitrates concentration continuously decreases due to low solubility at the high temperature state. Optical emission spectroscopy was used to understand the possible reaction mechanisms of NOx and hydrogen formation. First figure shows typical O spectra of nitrogen discharge in water. Second figure shows possible reaction pathways for the formation of NOx, oxygen, hydrogen and ammonia, based on optical emission spectroscopy. This study presents a novel plasma catalyst integrated system for highly selective and massive ammonia production from reagents of only water and nitrogen using renewable electricity. The plasma catalyst integrated system provides the basis for a novel and alternative path for potentially localized ammonia production. The demonstrated process is a unique combination of plasma-liquid interaction for the cogeneration of hydrogen gas and nitric oxide and a catalyst for the reduction of nitric oxide by hydrogen to produce ammonia. 300 to 400 times high ammonia production than those previously reported for plasma and electrochemical technologies, and high selectivity were achieved with this unique system. This process will provide a breakthrough in the ammonia economy that may drive green solutions for sustainable energy demands. The presented work was published in ACS Energy Letters. Thank you for your attention. For question or comments, please visit my personal blog, plasmascholar.com.